So why should we care about unifying quantum and classical computers? Well, we all want to reach practical quantum computers that can solve hard and useful problems that are out of reach today for classical computing technologies. And when I say all of us, well, of course, I mean everyone. But in particular, there are these two communities that are coming together now. The quantum community, who has been dreaming about building a quantum computer for 40 years now, and the high-performance computing community, who's been in charge of exploring new computing devices, new regimes, and pushing the limits of computing for many decades now. So these two communities are coming together for the first time to bring quantum computers to reality, which I think is truly, truly fascinating. But while the progress in the field in the last decade has been really amazing, with more and more qubits in a single quantum processor, with higher and higher quantum volumes, and with more and more resources being invested in the field, we also have quite a long road ahead of us. And there are many challenging obstacles along this way. To overcome some of these challenges, it became clearer and clearer in recent years that tight integration between classical and quantum computing is going to be needed. We view this sort of like a turbo engine that's going to help us drive faster towards the future of the field. You see, if we want to reach a useful application, there are many stages that are required, and actually almost all of them require this tight integration that we're talking about. So when you just start working with a new quantum processor or a QPU, you need to calibrate it. That means that you need to find and extract the parameters of the quantum processor, and this is actually done by a classical processor. And this is in fact one of today's biggest bottlenecks for both performance and uptime of quantum computers. And so we can really accelerate it via the right integration between quantum and classical. Next, even after the QPU is calibrated, the error rates in quantum computers are still very, very high. This is in fact the #1 challenge in quantum computing today. To overcome these errors, first, sophisticated error mitigation techniques must be employed, where classical optimization, again done in the classical processor, of the operations that we perform on the QPU can be done to sort of avoid some of these errors. And then ultimately, quantum error correction techniques should be used to eliminate errors actively. That means by constantly probing the QPU and having heavy classical processing decode the errors in real time so that we can correct these errors in real time. This is actually an extreme example for the need for very tight quantum classical processing integration. And finally, the QPU is really an accelerator. So quantum processors are better than classical processors, but only for some problems. So when we run a full application, it will almost always have to be a hybrid application, again, requiring the right integration. So now we see that we really need to bring it all together and build unified quantum classical architectures where we can run efficiently complex quantum classical workflows. And I think this is a really, really fascinating problem to work on. And this is actually what brought us to start the company at Quantum Machines. And today, to very excitedly partner now with NVIDIA, as we'll tell you about today. At Quantum Machines, our mission is to accelerate the realization of practical quantum computers. How do we do this? Well, it turns out that at the heart of quantum computers, there is actually classical hardware and classical software. While we all know about the quantum processor, where we have the qubits and the entanglement and all the quantum magic, there also must be another system, a classical system, that tells the QPU what to do. This is called the control and orchestration system, and communicates with the QPU with fast radio frequency signals. At Quantum Machines, we're developing this control and orchestration system for quantum computers. We've developed a unique platform that we call the OPX that can control a variety of quantum processors and devices and bring out the best performance of them. At the heart of our technology, we have developed a new type of processor that we call the pulse processor. This is not a quantum processor, it's a classical processor, but it's the classical processor that communicates with the quantum processor and operates it. And for the first time, we brought classical compute engines into the heart of quantum control by integrating these classical compute engines into the PAS processor so that we have classical compute as close as possible to the QPU. The latencies between the QPU and the controller that we can achieve this way are down to the hundreds of nanoseconds. The PAS processor is then programmed using our unique quantum classical programming language, QA, which is a low-level programming language that is used now by all of our customers around the world to develop their QPUs and extract performance out of them. Today, we provide an entire control stack that includes cryogenic control electronics, room temperature controllers, and several important programming and software infrastructure tools. We are a team of more than 130 people spread in 7 countries around the world. We have one of the biggest patent portfolios in the field. We're leading the Israeli Quantum Computing Center, which will give low-level access using our control stack to quantum devices, variety of quantum devices, to the entire community. And we have over 200 customers around the world, all working on developing quantum processors and requiring more and more control, more and more advanced control every day. So it is really, again, our unique control system and the PAS processor that integrated classical compute engines very close to the QPU to achieve these very low latencies of hundreds of nanoseconds. So we really pioneered the classical quantum integration. But this is not enough. We really need now, it's really critical now that we integrate with much heavier classical compute resources like GPUs and HPC clusters to really bring the full vision of quantum classical computers to reality. And there are actually very stringent requirements here. So again, latency is of course the key element. Cost scheduling and of the quantum and classical resources is another key aspect. And finally, we want to program it all together from a single programming platform. So since we met the NVIDIA quantum team, we immediately felt the connection and the alignment around this vision and around the wish to create enabling technology around this integration. So today, we're introducing DGX Quantum together, bringing together the world's most powerful quantum controller and most powerful accelerated computing platform to realize the full vision of quantum classical computers. DGX Quantum will have an ultra-low latency interface that allows the controller and the GPU to deliver unprecedented performance in quantum classical processing. And on top of it all, seamless hybrid programming via CUDA and CUDA Quantum, which will compile to QA and then run on the OPX, is sort of the cherry on top that will allow us to utilize this tightly integrated platform very, very productively. We strongly believe that this technology will allow quantum computer developers and HPC centers to really enjoy performance-defining technology out of the box so that they can push the field forward faster than ever.